Aloha mai kako. This is Module 14, Mauna Kea. As a reminder, your Module 14 quiz is due Monday at 8 a.m. In today's lecture, we will be going over Mauna Kea's profile and stage in life, the history of glaciers on Mauna Kea, and Akua of Mauna Kea. Here is the view of Mauna Kea on the right and Mauna Loa on the left from the Hilo Airport. From this image, it's pretty obvious that Mauna Loa and Mauna Kea have different profiles. Mauna Kea, Mauna Loa. We have viewed this image a number of times in class. As a review, Hawaii is the product of hotspot volcanism. The current hotspot is located at Kamaehua Kanaloa Seamount, formerly known as Lo'ihi. This process has also been described as the conveyor belt model of Hawaiian volcano volcanism. As you move further away from the hotspot, the volcano's age increases, and they begin to undergo erosion and evolution until they are completely beneath the surface, like we have seen in Papahanaumokuakea. The concentric structure of the hotspot explains how Hawaiian volcanoes go through stages. The hotspot is more like a hot column, and except at the very top it is solid because pressure prevents the rock from melting. The middle of the column produces more magma than the edges. Kamaehua Kanaloa is just moving into the zone of high magma production. Mauna Loa and Kilauea are directly over the central part, so they erupt frequently. Mauna Kea and Hualalai have moved off the middle part and erupt less frequently. And Kohala and Mahukona Seamount are pulp. They're done erupting. This geologic map shows and distinguishes between the different ages of various lava flows produced by Mauna Kea. The most recent of the Mauna Kea flows is shown in yellow, all of which are 4,000 to 5,600 years old. This is the last time Mauna Kea erupted. Mauna Kea is considered to be dormant, not extinct. According to the National Park Service, Mauna Kea still has a chance that it will erupt again in the future. However, the periods between eruptions is much longer than other volcanoes on Hawaii Island, and as such, it most likely won't occur in our lifetime. Pu'u Kana Kaleo Nui on the northeast flank is perhaps the youngest eruption site on the volcano. If we look at Pu'ukana Kaleo Nui viewed upslope from the east, it's about only 4,000 years old. The dark colored deposits partially surrounding and mantling Pu'ukana Kaleo Nui consist of tephra and ejecta blocks of lava, mostly 10 to 50 centimeters in diameter but as large as 3 meters long. Some of the ejecta are from underlying lava flows that were erupted more than 65,000 years ago from the Hamakua volcanics. The light-colored surface below the cone consists of lava flows that are not mantled by the explosive tephra blocks. This photo shows a current profile of Mauna Kea. However, if we were to take a few steps back in time, beginning here with the red line, this is a hypothetical profile of Mauna Kea at the end of the main shield stage, approximately 250,000 years ago, when the hotspot was located closer to this region. Here you can see that the active magma chamber was fed from a strong supply from deep in the magma chamber. The brown line in this next image depicts what Mauna Kea might have once looked like during the Hamakua flows that occurred approximately 65,000 years ago. By this time, the magma chamber started to solidify and the supply from the mantle was waning. Finally, the most recent stage of volcanism fed Laupohoehoi flows between 65,000 to 4,000 years before present. How the now solidified magma chamber this means that eruptions have no place to pause and degas, so they arrive at the surface with a lot of gas and relatively cool, and therefore the eruptions are more explosive than typical Hawaiian eruptions. A greater percent of the erupting material goes into building the cone than feeding the flow. A greater percent of the material goes into building the cone than feeding the flow, and the result is a high cone with a bumpy mountain profile. Mauna Kea's recent eruptions probably resembled those of Paracutin in Mexico, according to Ed Wolf, who published the most extensive geologic study of Mauna Kea. Next, let's take a view of Mauna Kea from Mauna Loa. You may be surprised to learn that there is evidence of a large glacial presence on Mauna Kea. Hawaiian mo'olelo have a long history of describing snow and ice on the Mauna. Glacial evidence was first described in the Western geological literature by Reginald Daly in the early 1900s. We are going to learn more about the evidence used to infer glacial history and climate both locally and globally by zooming into the area highlighted in yellow. Here's an image of a moraine and or outwash deposit. A moraine is a material left behind by a moving glacier. This material is usually soil and rock. Just as rivers carry along all sorts of debris and silt that eventually builds up to form deltas, glaciers transport all sorts of dirt and boulders that build up to form moraines. To get a better idea of what moraines are, picture yourself with a toy bulldozer on a lawn that has a bunch of dry leaves all over it. When you run the bulldozer through the leaves, some of them get pushed aside, some of them get pushed forward, and some of them leave interesting patterns on the grass. Now think of these patterns in piles of pushed away leaves, moraines stretching for kilometers on the earth, or in this case, along the slopes of the largest mountain in Hawaii. The most recent of the glacial deposits covers much of the summit or platform of Mauna Kea. Here in this image, you can see how arms of the glacier flow between some of the large cinder cones. All this gray rock that covers the summit platform is glacial moraine, debris of all sizes broken and carried by the most recent Mauna glaciers. It is estimated that the largest glaciers on Mauna Kea were no more than about 170 meters thick, and the last only achieved a thickness of about 100 meters. Typically, glaciers begin to flow when they reach a thickness of about 50 meters. So clearly, the ice on Mauna Kea was more than thick enough to begin flowing away from the summit, sculpting the rocks beneath into the forms typical for glaciated areas. Other glacial evidence includes a'a flows that have had their tops scraped off, and those tops are glacial striations. Similar striations in the continental places that are currently ice-free led geologists in the 1800s to propose the idea of ice ages. At least a few eruptions took place while there was ice, and the interaction between erupting magma and melting ice was explosive. Hyaloclastite, now altered, the product of explosive lava-water interactions. Hyaloclastite deposits form by the forming of or intrusion of lava or magma into water, or in this case, ice, where it's shattered into small angular fragments. Here is an image of pillow lavas, the product of non-explosive lava-water interactions. Lava flowing beneath water produces pillow lavas. This image was taken not far below the summit. One flow must have chilled against ice, causing it to cool really quickly and become almost glass-like, producing some of the best pohaku ala in all the Pacific. This lava is known as Hawaiiite, a Hawaiiite flow. Several quarries for the mining of this rock for ko'i, or adze, can be found near the summit along the ice contacts. Consider the difficulties faced by Hawaiians who live near sea level and who trek to the cold summit of Mauna Kea and remain there for quite some time to mine and chip stone tools. Here we are going to take a look at 3 separate deposits that have been mapped by geologists. The Pohakuloa flow shown in purple has been age dated to about 300,000 to 240,000 years before present. Waihu in green occurred 200,000 to 110,000 years ago, and Makanaka in blue occurred about 80 to 15,000 years ago. Now let's take a closer look at what these flows tell us about local and global climate. This figure here depicts how these Mauna Kea glacial deposits fit with the world temperature curve. We're going to slowly go over this figure in subsequent slides. Hint, this would be a good figure to include in a quiz. The x-axis shows an age thousands of years before present, with 0 or present on the right-hand side extending to 500,000 years before present on the left. The y-axis shows the relative percent of the ratio of oxygen isotopes. But what is an oxygen isotope? To understand this figure, we need to first have a quick chemistry lesson on oxygen. Oxygen, like all elements, come in heavy and light varieties, also known as isotopes. Distinguishing between the 2 oxygen isotopes is useful for understanding long-term changes in climate. Like all elements, oxygen is made up of a nucleus, of protons and neutrons, surrounded by a cloud of electrons shown in blue. All oxygen atoms have 8 protons, but the nucleus might contain 8, 9, or 10 neutrons. Light oxygen, oxygen-16, has 8 protons and 8 neutrons. It is the most common isotope found in nature, followed by much lesser amounts of heavy oxygen, oxygen-18, with 8 protons and 10 neutrons. The ratio or relative amount of these 2 types of oxygen in water changes with the climate. By determining how the ratio of heavy and light oxygen in marine sediments, ice cores, or fossils is different from a universally accepted standard, scientists can learn something about climate change and those events that have occurred in the past. So let's return to this figure again. One more figure before we go back to that plot. Taking a closer look at the water cycle, it has been shown that ice and glaciers have less oxygen-18 than seawater. To understand why this might be so, we need to think about the process of glacier formation. The water or ice in glaciers originally came from water that evaporated from the oceans as vapor, and then later fell as snow and became compacted into ice. When water evaporates, the heavy water that contains oxygen-18 is left behind, and the water vapor is enriched with light water with oxygen-16. This is simply because it's harder for the heavier molecules to overcome the barriers to evaporation. Thus, glaciers are relatively enhanced in oxygen-16, while the oceans are relatively enriched in oxygen-18. This imbalance is more marked for colder climates than for warmer climates because more oxygen-16 is trapped on land as ice and does not return to the ocean as runoff, as would happen when the world is warmer. In fact, it has been shown that a decrease in 1 part per million of oxygen-18 in ice reflects a 1.5 degrees Celsius drop in air temperature at the time it originally evaporated from the oceans. So returning back to this plot of global ice volume, we see how the ratio of oxygen-18 to oxygen-16 is used for a proxy for world temperature. As a reminder, the ratio of oxygen isotopes is shown on the left. Larger values at the bottom of the y-axis, smaller values at the top, so a larger value would be reflective of more oxygen-18. When it is cold, again, oxygen-16 is more preferentially evaporated, so oxygen-18 in the ocean water goes up, as well as oxygen-18 in ocean sediments. Here you see glacial periods, or periods of high ice periods, coincide with max values of oxygen 18. So each of these valleys here, here, and here are representative of colder periods that have more oxygen 18 and therefore more ice. So you see in this figure that Pohakuloa, Wai'ihu, and Makanaka glacial deposits all occurred when ocean water was enriched with oxygen 18, and there is more ice documented around the world because the climate and global temperatures were colder. This map here shows what the world would have looked like during Makanaka time. This map shows a reconstruction of glacial coverage during the most recent glacial maximum period, 18,000 years ago. Look at how far south in North America ice extends. For some of you, ice could extend into where your home now is, on the continental US. There are also large extents of ice in Aotearoa, Australia, and South America. Other notable features on Mauna Kea are the large number of scoria cones. We learned previously about scoria cones, but as a reminder, a scoria cone, also known as a cinder cone or a pyroclastic cone, is a small volcanic feature that forms from solidified lava fragments that fall around a volcanic vent. Scoria cones are the most common type of volcanic cone and can range in height from tens to hundreds of meters. They are often found in the flanks of shield volcanoes, stratovolcanoes, and calderas. Another notable feature on Mauna Kea is Lake Waiau. Follow this link and you will learn from Floyd McCoy, a geologist at the University of Hawaii, about how Waiau formed and the role that the glacial history of Mauna Kea played in its formation and its current presence. Another name for Mauna Kea is Mauna Kea. In the next subsequent slides, we're going to take a closer look at some of the cultural aspects of Mauna Kea or Mauna Kea through the lens of Native Hawaiian storytellers, practitioners, and activists. Mauna Kea is known to reach into Vau'akua, the realm of the gods. In ancient times, Vau'akua was kapu or forbidden to everyone but the highest ali'i or chiefs. At the top of Mauna Kea in Vau'akua sits Lake Waiau, given the name for the goddess that birthed and created the lake. Waiau was used as a place of knowledge and learning for the ali'i. The top of Mauna Kea sits close to the heavens, so the ali'i would have gone up there to worship, pray, and learn. Using the reflection of the stars in the glassy water of Lake Waiau, the ali'i would study the stars to be used for voyaging and navigation. The seasons for planting and harvesting. The water of Lake Waiau is also known to have healing properties. The vai is collected and used for ceremonies and healing. Mauna Kea is home to many akua which give life to our sacred mountain and the complex hydrological and ecological ecosystems that live within. The next few slides will be independent learning, and you will use a series of links to learn more about Mauna Kea through the various akua and mo'olelo. We will start first by listening to a short podcast. Oh, sorry, I took that podcast out. So we're going to start first by having you folks follow this link and learn about Poliahu and her relationship with Pele. So please copy and paste this link into your browser. Next, you're going to learn about Poliahu and Ku Kahau'ula, her partner and her lover. And then we're going to end today's lecture with a short film called Like a Mighty Wave that documents the ongoing struggles at Mauna Kea related to the proposed construction of the 30-meter telescope. Please watch this film. As a reminder, you'll have only one quiz this week that covers both the geological and cultural aspects of Mauna Kea covered in this lecture. Please use all the materials and links provided today to help you prepare for your quiz. As always, your quiz is due at 10 a.m. on Monday morning. Good luck!